thinking how lucky you are, because I never had an engineer to talk to, and I was, no, I had no idea what they were talking about.
You have to learn
It's something else.
during the...
No. I learned it now, but you can learn it now. You know each other now, and so you can just ask each other, yeah? And debate and things like that. And you see that you mathematicians, you have to be very precise. Yeah? With engineers, you have to be precise with units. And we mathematicians always put a 1 there, doesn't care. Doesn't care. Without loss of geometry, we put a 1 there. Then the units are not correct and things like that, we don't care. Yeah? But there is a story there. There is also a story. I worked also with Wageningen, not with Wageningen, I also worked with Wageningen, but this was with Eindhoven, platooning. So letting cars run very close together, yeah? So this car knows where the position of this car, the velocity, acceleration, knows everything of that car. And that you would think, and I heard about it when I was already a student, and then you were thinking, okay, nice, but you have to have equal cars, yeah, because otherwise, yeah, your dynamics will be, your Ford car will have a completely different dynamics than a Ferrari, yeah. So how can you model? And it was modeled as being the same model, because that made it mathematically very simple. But then I learned, because they had done tests near Eindhoven and things like that, so it's not really autonomous driving, yeah? It's adaptive cruise control, it's called, yeah? So you drive really with a short distance from each other, and the idea is it's still safe and there can be more cars on the highway. And then I asked them and they said, okay, but now the clever thing is that if you have this adaptive cruise control, then you have an internal controller that makes your car behave like a standard car. So that's the idea. So they build the company and you switch on the adaptive cruise controller. That's of course a controller designed for your car, basically for your type of car. It makes it behave like a standard car. And they have defined then what is a standard car. And there were parameters in. I said, okay, yes. I said to Jeroen Ploeg, where I was, what's the value of this parameter? Oh, we did experiments, it's just 1. So you just could put 1s everywhere, it's just amazing. I always tell to students, oh, I put a 1 there, but in reality this is never 1. And then you meet a real engineer and you ask what is the constant and they say 1. It's amazing. This is again for the same course in February, so I have not changed the abstract differential equation. So it goes into math theory, semigroup, support, Hamiltonian. It's somehow that triangle, called the triangle of death or something like that. Does it work? Yeah. So again, I go to the vibrating string, because this is my example, and you see the mu has changed into a rho, the z has changed into a zeta, the u has changed in a w. Somehow, but this is consistent with the blue book. So there is somehow some consistency somewhere. And then of course we want to existence of solutions. So basically this whole semigroup theory and the math theory is there to prove that you don't talk about what mathematicians say an empty set. If I don't have a solution, then I can argue a lot of things, but then in mathematical terms everything is true. Everything is true about the empty set. So if I don't have any solutions, I could claim anything. So the whole problem, and so this problem for nonlinear PDEs has not been solved. That's the open problem. Do I have a solution? So here, basically this whole mathematical theory, semigroup theory, port Hamiltonian, this is a port Hamiltonian system, is there to tell, yes, hooray, we have a solution. And that's the only aim of this whole setup, of this whole mathematical theory at the beginning. Yeah? We are not, and I always say, you always have this question for a linear ordinary differential equation, but that you had in your, I think in your first year already, that and maybe in high school, that y dot equals 5 times y, that has a solution. And if you fix the initial condition, then it has a unique solution. And then for nonlinear ordinary differential equation, so if I have x dot equals f of x, and x is a vector or something like that, then you only need Lipschitz continuity of f, and I have uniqueness of solutions, which is a very mild condition, so nobody in nonlinear control theory ever talks about existence of solutions because you have them. It's only if you take f as the square root of something that you have maybe to think about, but if you just, so you basically there, in ordinary differential equations you get existence of solutions for free, you could say. Yeah? They're just there. You don't need extra conditions on your system. Yeah? They could be a nonsense model, but you still have solutions. Yeah? In PDEs that is believed, okay, for the mathematicians, I could give you a model without a solution. So, you can just have that. Yeah? And as you know, I like counterexample and things like that. So I can write down a PDE which does not have a solution. I even constructed a nonlinear one where I can prove I don't have solutions. Beautiful. Yeah? So you have to be careful. You don't... Okay. There are two messages here, basically. And let's think... So we have the bad news first. The bad news is that you, even for linear PDEs, you have to do work to get existence of solutions. Yeah? You don't have it for free. You don't have it for free. The good news is that for port Hamiltonian systems, you have it more or less for free. But okay, that takes a while to get there, but that is the bottom line. So linear port Hamiltonian systems, and definitely on a one-dimensional spatial domain, I still have to prove it in more than one spatial domain, but that's one of my projects. I mean 25 students. No, that's, I know what to do and things like that, but it's still not settled there, yeah? But okay, one-dimensional discourse. I just follow my own slides, yeah? And then maybe you say, well, we know this. So first of all, you have to think, because I want to write it in a state space formulation, I have to think about state in state space. And definitely, and we have seen it, idea of the state. That's good to have that. What is the meta view on a state? And when people told me that when I was a student, I had no idea, it doesn't help anything. But basically the state is, if I know my state now, I know what the system will do. So it's the information which I need now to tell what the system will do, basically the next time step. But since I am continuous time, it means whatever you have, yeah? So it's information which I need to have. Now, if you have this, then you see how you could, you could have a mass spring system, and I put there capital M because this Y could even be a vector or something like that. But then I need my position and my momentum or the velocity to predict precisely what I will do. If you don't give me the values of this, I cannot tell what the system will be at the next time step. So I have to have this motion. So, and then your state space, okay, this is just if Y is a scalar, then the state space is just R2. Yeah? I need two elements, and I can group them in a vector, and then my state space is just n. Okay, what's the space of vectors of two elements? That's R2. If I want to have a complex value, but then of course the physicists start to, what is a complex position? But then you could also write here C2. Yeah? You can be a complex situation, but then it's still not in the complex numbers. Okay, and then of course, what is the state for this? But we already know the answer, yeah? So I can just go quickly over that. So what's the state for this system? Now, yeah, you could say, of course, position and velocity, like you had, but we had this discussion before. But you could also take the strain and the momentum. And that is in the Port Hamiltonian, you take these later too. And the whole change, what we had to do, Ruth and I had to do in Birgit, is to get somehow that state out of our mind and the second state into our mind. Yeah, just a change of thought, yeah? Viewing. Or, yeah, you could even think of more. Eh? It's just, the state is very general. This is what I have to know, say, basically, what the system will do. So you could put a t in front of it, you could take a linear combination of these two. Yeah? You have freedom, yeah? There is always a freedom in choosing a state. Yeah? Even if you think these are the two, then in which order do you put them? So there is always a freedom. But this is, whatever state you choose for a partial differential equation, it will become a function. You freeze time, basically a state is a situation of the system frozen in time. But even if I freeze time, I still have my spatial coordinate. So this is my state at time t. I can talk about the state at time t, but I still have a function. I still have this position. Of course, it could be zero, but okay. It's still a function. Even if it's zero, I have to say, no, it's the zero function. Not the zero number, but the zero function. So that's already important, and that is in every partial differential equation, that your state becomes a function. And a function of the spatial variable. Yeah. Then of course I need a function space. Yeah, my states are functions. Now where will the functions lie in? Yeah, in a function space. I'm filling just one hole with the other. Huh? So I need a set of functions, a set of spatial functions. So in a sense my state is in between 0 and 1, so I need functions defined on the spatial interval 0 to 1. And now, there are a lot of spaces describing functions, say basically from the interval 0, 1 to R or R2. I could say, oh, they are continuous functions, oh no, they are Chadwick differentiable, they have to be piecewise continuous. Yeah, you can choose a lot of things. Eh? That's again a choice. Eh? You see somehow from your PDE in your idea of state that I need a function, a spatially dependent function, but in which class? In your class, if I just have two numbers, yeah, then there are just two numbers, then R2 is very logical. Yeah? But here I'm talking about functions, and then I have a lot of freedom to choose. So the choice of the state space can differ from application to application. Even if you are talking about functions from, say, the interval 0, 1 to R. A lot of systems with time delay, people take as state space the continuous functions. Choice. Now, have you now figured out by now what this is? L2, AB values in R2? I think so, or not? Just
The space of square integral function.
which values in R2? So I always say, and now I'm just looking at the mathematicians here, yeah? I say, oh, this is the space of square integrable functions. But then the mathematicians say, what do you mean by integrable? Because what is an integral? No. Fourier just also said something, just square integrals. Fine. Then of course you can start, so I could give a whole course, but then you are here till next Monday or something like that, what I mean by an integral. So there is a whole theory thinking what are square integrable functions? You say, well, that's simple. I just square them and I calculate the integral. If there's not infinity coming out, then it's integrable. Yeah, but how do I calculate an integral? Okay, that is the whole theory of Lebesgue integration theory. And there the L is coming from Lebesgue, and say 100 years ago, Lebesgue really set up, because you know the integral as Riemann sums probably, that you integrate. That was not good enough because you could have weird functions. And the standard weird function is the following. I make some function 0 on the rational numbers and I make it 1 on the non-rational numbers. And then I want to know what is the integral. And then there are two answers. It does not exist and it does exist. And then if it exists, what's the value of? Yeah, I don't. It's 0 or 1. I have not remember how I defined it now. 1 on the rational.
1 on the irrational.
Ah, then it's 1. If I have an interval 0, 1.
We did a similar example in a note.
Yeah, but it's weird. But people started, and that you really see that is somehow dominant in the 20th century. That people start really to think very deep. We know this concept, but do we really know this concept? And then the funny thing is that you basically have to throw everything again and just start again. And basically where Lebesgue integration start is just making the function 1 on the interval AB and saying the integral of that is B minus A. And there it starts. And that is somehow, okay, everybody believes that. And if you believe that, then you can also calculate after a long course Lebesgue integration theory, normally called, that the integral from 0 to 1 of this strange function is also 1. Weird, yeah? But they are in this space, yeah? But for engineers, I always say, yo, you're square integrable. Yeah? But they can have jumps, and it's good to realize that jumps are allowed. Yeah, so there is no continuity here. That's basically, it's very good to have that in mind. But this is just a choice. And maybe important here to say your problem dictates this choice. Should dictate the choice. Yeah? And we will see that this L2 is perfect with the energy. If you take this state, you get another space here. And that was always the problem also, because we knew that the state space L2 was not good enough, but then we were talking about this one. For this, it's perfect. Yeah, it's just the problem dictates, or the problem, somehow the problem, the PDE I would say, or where it comes from, dictates somehow your state space. To some extent, but if you know my problem is only well defined for continuous functions, and this should be continuous functions. Yeah? It's just really always a choice there. Yeah? That's just what I want to point out. There is a choice in your state. And then, okay, it's our function, but then there is a choice in your function space, which is not there in finite dimensions. Yeah? It's not there. Okay, there we have it. And this is Rn, and this is then the norm in Rn, because the F takes values in Rn, so this is for every zeta here, this is just a factor in Rn, so this is just the norm in Rn. That's easy. And you are really making notes. I could also email you this. No, you may make notes, but then I don't. Then I have to pay attention that you are not. That I don't go too quick. Okay. And now we get a Hilbert space. Oh, I already heard on Wednesday. There was all these Hilbert spaces and things around, and terrible. Sleepless nights of it. A Hilbert space is an inner product space. In an inner product space, okay, I'm just saying that L2 is a Hilbert space. And what does it mean? There is an inner product. I don't know if I have really written down the properties, what an inner product is, but this is the inner product in two functions. So I have two functions and with values in Rn. So this is just the transpose vectors I always make as column vectors. And then I just integrate. This is the inner product. Also a story about this. This inner product, you could say, was already known since Fourier. But he did not call it an inner product. But he was working with it. Improved all kinds of things and that these signs were orthogonal to each other. It was only at the end of the 19th century, and I think it was with Hilbert himself, I'm not 100% sure who did it, say end of the 19th century, beginning of the 20th century, that people started saying, hey, wait one moment, what I'm doing with vectors, that vectors can be orthogonal to each other, I can also do with functions. I have to think of an abstract notion which is then called an inner product. But for instance, if this outcome of this integral is 0, then it says that f and g are orthogonal to each other. And so the inner product in Rn is just this, and without the integral. It's just this, you just do the transpose of the one and then you do it times the other, that's the inner product. But people realized that all these things what Fourier did, that the Fourier series was nothing else than decomposing it in an orthonormal basis. Oh, that was just a lot simpler. So this unification, this unification really started really in the 20th century. But this is a Hilbert space or L2 is a Hilbert space, and it has, here it is. The funny thing is, of an inner product, you only need a few properties. Something is an inner product if these properties hold. If these properties don't hold, then it's not an inner product. Not easy. And this is then for real functions, If you have complex valued functions, then it becomes a complex conjugate and things like that. But it's just saying if you have the sum of the two, then you can calculate the sum, you may interchange them. And if you have, that's the most important one, is if you have f unequal to 0, the inner product of f with itself is always positive. Now, and then if you want to prove this for L2, then you have also first to introduce the equivalence classes, etc., etc. I don't go into that. But this is somehow intuitively it's clear, because if you have this, the transpose of f times f itself, and it's the absolute value squared, I integrate the square function. If it's not 0, then it must be positive. Not so easy. I tried to find who introduced the name Hilbert space.
It was Weil.
And was it Weil? Because I was not so 100%. What I read, it could be Weil, but it was also in the students of Hilbert, because Hilbert was all the time talking about L2, and then the students and PhD students of Hilbert just called it then always the Hilbert space. There's Hilbert again over this class, but it can officially in the first publication it could be Weil. I have not found it yet. Okay, I could. Okay. But a Hilbert, but there is another. So it should be an inner product space, but not every inner product space is a Hilbert space. And then always the norm is defined like this. Yeah. So just stop like this. So in a Hilbert space or in an inner product space, I always have a norm. And a norm tells of an element. So if I just have an element, it can be a function, it can be a matrix, it can be anything. But a norm just gives a positive real number to it. And it basically tells how large it is. That's a norm. So it needs to have nice properties, so if I multiply and say my element with 2, then the norm also becomes twice as large. And the norm of the negative is in there. Okay, but basically it follows from these properties that this is a norm. And you have a triangular inequality for that norm. It's basically, a norm just gives a positive number into a quantity. And then this is really what is, say, the Hilbert space. So a Hilbert space is an inner product space with this last property. And the property is that if I have a sequence of functions, and here I'm talking about functions, and if I calculate the norm, and if when n and m independently, n could go on a TGV to infinity, and m could go on a sprinter into infinity. Doesn't matter how fast they go to infinity, independent of each other, but if they go to infinity, then they should become closer and closer. If that happens, then there should also exist an element to where they are converging to. Now the standard example where this does not hold is the rational numbers. If I make an approximation of square root of 2 by a rational sequence, so I just take the decimal expansion and I truncate it and I have a rational number, but you see it gets closer and closer to the square root of 2. But there is no rational number to where I'm converging to. So it really tells you somehow, and this is called completeness, and that your space is complete. All the elements which I can approximately reach are in there. That's basically what is it, yeah? And that's why with this inner product, the continuous functions are not an Hilbert space. Because what I can do with a continuous function, I can approximate better and better the step function. You see, if I have a step function, I make it smoother and smoother over a small area, but still I keep continuous. Then in the limit, of course you see more and more, and of course you have to calculate that exactly, that in this norm I go to 0, but that's not so hard. In this norm I go to 0, so these elements get closer and closer to each other, but what is the limit? That's the step function. But the step function is not a continuous function. So that's why the continuous functions are not a Hilbert space. Whereas they are an inner product space, and this is well defined on continuous functions. Yeah? And so to prove that L2 has really this property, okay, that's really hard, because you have a function, you don't have a limit, but there has to be a limit. Yeah? It tells you the existence. There is an F to where I'm converging.
The continuous functions are complete, but not for this.
Not with this inner product.
Not with this
Yeah.
one.
If I take the continuous functions with the supremum norm, then it is complete. Then it has this property. So it really depends on the norm you choose. It's always to realize that. Which is the norm? What is the space? Yeah? But the continuous function with this norm is not complete. But I can find another norm for which it is complete. Yeah? And that norm, the supremum norm, is not coming from an inner product. Some wording, a space. So if I have just a norm, and then it's not this, I just have a norm, and this holds, then it's called a Banach space. So a Banach space is an extension, is a larger class of systems than a Hilbert space. Hilbert space, the norm comes from an inner product. In a Banach space, the norm need not to come from an inner product. Yeah, it's just so much functional analysis behind it, yeah?
Continuous function is in Banach space. Continuous function is Banach.
Is a Banach space, yeah. With the supremum norm. Yeah? You always have to say the continuous function with this norm is a Banach space. The same, but if you talk about L2, this is the standard inner product on L2. Yeah? So you never have to say, oh, L2 with this inner product. Yeah? L2 comes together with an inner product, but that is just, okay, after so many years, yeah. They are married already that long, they are seen as one pair, yeah? Yeah? a picture. This is a picture of a solution set, you could say. And we will come back to it as kind of intermission, a break picture or something like that. But you see states, the blue line is a state and the black line is a state. Yeah, state is a function of the space. Yeah? And if I just look at my solution of a PDE, which depends on time and space, then the state is just, I take a fixed time and I just cut in this plane. Yeah, so this is the state at t1/2 and this is the state at t1.5.